Hi everyone, my name is Swami. In this video, we are going to discuss about some of the questions related to ESR spectroscopy. Now, let us see the first question. Now, the number of lines exhibited by high resolution EPR spectrum of the species CuEn twice 2 plus is, okay, here in this one they have given the nuclear spin, that is I value of the copper, that is 3 by 2, and also they have given I value for nitrogen, that is 1. Now here, okay, this question was asked in December 2012 in CSIR-NEET, okay, for 2 mark. Okay, so now here they have given option A, that is 12, and option B, that is 15, and option C, that is 20, and option D, that is 36. Okay, so now let us solve this question. The number of ESR lines for CuEn twice 2 plus. Okay, now if you draw the structure of this copper plus 2 complex, okay, this is a copper plus 2 complex, Cu plus 2 complex. Okay, now in this Cu plus 2 complex, here copper plus 2 is the central metal ion, and which is attached to the ethylene diamine. So here means ethylene diamine. So this is CH2, and this CH2, NH2, and this is NH2, CH2, and CH2, NH2. Okay, so it is a square planar complex. Okay, here we can observe copper plus 2, which is attached to the ethylene diamine bidentate ligand. So it is a bidentate ligand. Ethylene diamine is a bidentate ligand. So if you see this complex, okay, there are two kinds of nuclei which is ESR active. So one is copper. Okay, so here this copper is ESR active. So this copper plus 2 is active, and this nitrogen is also, okay, this nitrogen is also active. Okay, so these hydrogens, okay, these hydrogens are inactive. So according to Drago's rule, okay, in this complex, okay, copper is active and nitrogen is active. So if the nitrogen is active, hydrogens are inactive according to this Drago's rule. Okay, now let us calculate the number of lines that we have observed in high resolution EPR spectrum. So now here we can apply 2Ni plus 1 rule. So for copper 2 into the number of copper atoms, that is 1 into I value for this copper. Okay, they have given for copper I value is 3 by 2. For nitrogen they have given I value is equal to 1. So 3 by 2 plus 1 for nitrogen. Okay, you can simply apply 2n plus 1 rule. So here, okay, 2 into number of nitrogen atoms. Okay, there are 4 nitrogen atoms which are attached to the copper plus 2. So here 2 into 4 plus 1. Okay, so here, okay, if you solve this one, so this 2 and these 2 will be cancelled out, and 1 into 3 plus 1, so that is 4 into, okay, 2 into 4, that is 8, plus 1, that is 9. So here the total 36. Okay, here we get 36 lines. So okay, here in the case of this CuEn twice plus 2 complex, so we can obtain 36 lines in the high resolution EPR spectrum. So the correct option is D, that is 36 lines. Now let us see the next question. Okay, now in this question they have asked the number of EPR signals observed for octahedral nickel 2 complexes is. Okay, so here they have given options. Option A, that is 1, and option B, that is 2, and option C is 3, and option D is 0. Okay, again this question was asked in June 2013 CSIR-NEET examination for 2 marks.
Okay, now let us solve this question.
So now here they are asking number of ESR lines for the Ni+2 complex. So this Ni+2 will contain the 3d8 electronic configuration. So it will contain the 3d8 electronic configuration. So in octahedral geometry, okay, the 5d orbitals which are present in this Ni+2, okay, these are the 5d orbitals which are containing 8 electrons. So these 5d orbitals will be split into Eg and T2g orbitals in the octahedral geometry. So these are the T2g orbitals and these are the Eg orbitals. Okay, now here in this one we have 8 electrons like this. So okay, this is the arrangement of electrons in the octahedral geometry of the Ni+2. So in this one we can observe 2 unpaired electrons in the case of Ni+2. So there are two unpaired electrons. There are 2 unpaired electrons that we have observed in the case of this octahedral Ni+2. So these 2 kinds of electrons, these 2 electrons will be having a spin of the electron that is minus s2 plus s. So it means minus 1 2 plus 1. So okay, it will be having spin that is plus or minus 1 and 0. So now let us see how these spin states will be split into different energy levels. Okay, in the absence of external magnetic field or in zero field splitting. So let us see the zero field splitting of this octahedral Ni+2 complex. So in the absence of external magnetic field, this plus 1, minus 1 and 0. Okay, these are the 3 energy levels of this spin will be having degenerated in state, okay, which is in B is equal to 0. So in the absence of external magnetic field. Now let us in the presence of octahedral field, okay, it means in the presence of crystal field, okay, they are split into 2 energy levels. So one will get the higher energy and this is a zero energy spin state. So it will be plus or minus 1 spin state. So it is in the presence of zero field splitting. Okay, zero field splitting is nothing but the splitting of the energy levels of the spin state in the absence of external magnetic field and in the presence of crystal field. So due to this crystal field, there is a splitting of the energy levels of the spins. So okay, due to this zero field splitting, okay, we can observe, okay, this doubly degenerated energy level, that is plus or minus 1. So in this zero field splitting, we can observe only one possible transition. So we can observe only one ESR signal in the case of zero field splitting. So here okay, we can observe one signal for octahedral Ni+2 complex.
So here the correct answer is 1. So okay, here the correct option is A. So A is the correct option for this question. Now let us move on to next question. Okay, for tetragonally distorted copper chromium plus 3 complex in zero field splitting results in the following number of Cramer's doublets. Okay, here they are asking the number of Cramer's doublets present in tetragonally distorted chromium plus 3 complex. Okay, now here okay, they have given option A, that is 1, and option B, that is 2, and option C, that is 3, and option D, that is 4. Okay, now which one is correct option? Okay, so this question was asked in June 2013 CSIR examination for 2 marks. Okay, this question was asked for 2 marks question. Okay, now let us solve this question.
Now in this one, okay, here they are given chromium plus 3. Okay, so this chromium plus 3 will contains the D3, okay, 3D3 electronic configuration. Okay, so there are there are 3 unpaired electrons. Okay, 3 unpaired. Okay, there are 3 unpaired electrons present in this chromium plus 3 complex. Okay, now for these 3 unpaired electrons, okay, we can observe the spin value, that is either plus or minus 3 by 2 and plus or minus 1 by 2. So here we can observe plus 3 by 2, minus 3 by 2, plus 1 by 2, minus 1 by 2. So these are the 4 kinds of energy levels of these spins we can observe for these 3 unpaired electrons. So let us see how these 3 electrons, how these 4 energy levels of these spin states will be split into doublets in the absence of external magnetic field and in the presence of crystal field. So let us see for that one. So this is the energy. Now in the absence of external magnetic field, so that is okay, this is plus 3 by 2, plus 1 by 2, minus 1 by 2 and minus 3 by 2. Okay, these are the 4 spin states of the 3 electrons in the chromium plus 3 in the absence of external magnetic field. Okay, B naught is equal to 0. Now let us see in the absence of external magnetic field and in the presence of crystal field. It means in the presence of zero field splitting. So in the presence of zero field splitting, okay, this plus or minus 3 by 2 will get the higher energy and this plus or minus 1 by 2 will get the lower energy. So this is in the absence of external magnetic field. So that is ZFS, zero field splitting. So we know that zero field splitting is nothing but the splitting of energy levels of these spins in the absence of external magnetic field and in the presence of crystal field. So due to this crystal field, there is a splitting of spin states of the energy levels of the spin states will be taking place. So that kind of splitting what we call as zero field splitting. So in this zero field splitting, all the energy levels are doubly degenerated. It means it can obey C or it can maintain the Kramers degeneracy. So in this Kramers degeneracy, we have 2 doublets. So here this is one doublet and this is another doublet. So 2 doublets. Okay, it means there are 2 doubly degenerated energy levels that we have observed in the absence of external magnetic field or in zero field splitting of the chromium plus 3 complex. So
now here the correct option is 2. Okay, so this B is the correct option for this question. Now let us move on to next question. The number of lines in Epr spectrum of CD3 is dash. Now here they have given the I value for the deuterium, that is 1. Okay, now here they have given options. Option A is 1 and option B is 3 and option C is 4 and option D is 7.
Now let us calculate how many number of ESR lines that we have observed in the case of CD3 molecule. So here, okay, this is a CD3 molecule. So in this one, okay, carbon is inactive because in general carbon 12 is ESR inactive and carbon 13 is ESR active. They should not mention they have not mentioned whether it is carbon 12 or 13. So you can consider as a carbon 12. So it is inactive. Okay. So here for this deuterium, okay, they have given I value is 1. So if I value is equal to 1, okay, we can simply follow 2n plus 1 rule. So now where n is equal to number of nucleus. So here 2 into where n is equal to number of deuterium atoms, that is 3 plus 1. So 2 3s are 6 plus 1, so that is 7 lines. So that is 7 lines we can observe in the case of CD3 molecule.
Okay, here the correct option is D. Now let us move on to next question. The Epr spectrum of free radical containing nuclei with a non-zero nuclear spin is obtained if the following selection rules are observed. Okay, this question was asked in December 2014 CSR examination for 4 marks. Okay, it is very simple question which is asked from selection rule. So here they have given option A, that is delta ms is equal to 0 and delta ml is equal to 0, and option B, that is delta ms is equal to plus or minus 1 and delta ml is equal to 0, and option C, that is delta ms is equal to plus or minus 1 and delta ml is equal to plus or minus 1, and option D, that is delta ms is equal to 0 and delta ml is equal to plus or minus 1. So let us solve this question.
So for ESR spectroscopy, okay, so the selection rule for ESR spectroscopy, okay, that is delta m s is equal to plus or minus 1 and delta ml is equal to 0. So this is the selection rule. Okay, this is the selection rule for ESR spectroscopy. So okay, here delta ms is equal to plus or minus 1 and delta ml is equal to 0.
Now here the correct option is B. So that is delta ms is equal to plus or minus 1 and delta ml is equal to 0. Now let us move on to next question. Okay, here the total number of fine lines and hyperfine lines expected for octahedral high spin Mn plus 2 complexes are respectively. So here they are asking number of fine lines and hyperfine lines for Mn plus 2 complex. So here they are given I value for manganese, that is a 5/2. So here they have given option A, that is 3 and 30, and option B, that is 5 and 33, and option C, that is 5 and 30, and option D, that is 4 and 24. So which one is correct? So let us solve this question.
They have given Mn plus 2. So for this Mn plus 2, so here in this case for manganese they have given I value, that is 5/2. So here in this Mn plus 2, so this Mn plus 2 will contain the D5 electronic configuration. So it contains D5 electronic configuration. It will be having D5 electronic configuration. So now these 5 electrons are unpaired electrons because here, okay, this Mn plus 2 in high spin state. So it is a high spin complex. So since it is a high spin complex, so that's why these 5 electrons are unpaired electrons. So here you can observe 5 unpaired electrons. 5 unpaired electrons. So now let us calculate number of fine lines and hyperfine lines. As we know that, okay, one electron will give the one fine line. So in that case, okay, here we have 5 unpaired electrons. So okay, these 5 unpaired electrons will use the 5 fine lines in the ESR spectra or Epr spectra. So where number of fine lines is equal to the number of unpaired electrons present in that metal complex. So here the number of fine lines is equal to the number of unpaired electrons. So number of unpaired electrons are 5. So there are 5 fine lines that we have observed in the case of this ESR spectrum of the Mn plus 2 complex. So here we can eliminate option A and option A. Here we have only 5 unpaired electrons. That's why only 5 fine lines we can observe. So in given options we have 5 in option B and C also. So we can eliminate option A and option D. So let us consider how many number of hyperfine lines that we have in this Mn+2 high spin complex. Okay, so number of hyperfine lines that is equal to the number of fine lines into 2Ni+1. So number of hyperfine lines is equal to number of fine lines into 2Ni+1. So okay, here number of fine lines that is equal to 5 into 2 into where n is equal to 1 because only one manganese, so 1 into I, so I value is 5 by 2, so 5 by 2 plus 1. So this 2 and this 2 will be cancelled out. So here we have 5 into 1 into 5, 5 plus 1, so that is 6. So that is 30 lines. So 30 lines, 30 hyperfine lines that we can observe in the case of Mn+2 high spin complex. So here the correct option is option C. So that is the 5 fine lines and 30 hyperfine lines that we have observed in the case of high spin Mn+2 octahedral complex.